Imagine a world where the oceans no longer breathe, where waves do not crash against continents, and storms have nowhere to form, where sunlight touches the surface of the planet, but finds nothing dark enough to warm. There was a time when Earth became a sphere of ice, nearly 720 million years ago, long before forests, long before animals, before even the first complex creatures took shape. The planet entered one of the most extreme climatic states in its history. Ice advanced from the poles toward the equator. Glaciers crept across continents that looked nothing like the ones we know. The seas, once open and restless, began to stiffen beneath a growing crust of frozen water. This was not a regional winter. It was not an age of cold confined to high latitudes. Geological evidence suggests that ice may have reached tropical oceans, possibly encasing the planet from pole to pole. Earth, suspended in space, reflected sunlight like a giant mirror. From orbit, it would have appeared pale and lifeless. A white planet circling a distant star. This period is known as Snowball Earth, a time when our world came closer than ever to freezing solid. And yet, life did not disappear. What followed would change the course of evolution forever. Asterisk before the ice. Earth was a different world entirely. The continents were gathered into ancient supercontinents, shifting slowly across a young planet, still restless beneath its crust. Volcanoes breathed steadily into the atmosphere. The oceans were vast, deep, and rich in microscopic life. There were no trees, no animals roaming land, no birds in the sky. The continents were barren rock and shallow soils, sculpted by wind and rain, yet beneath the ocean surface. Life was quietly transforming the planet. Cyanobacteria had already begun reshaping the atmosphere millions of years earlier through photosynthesis, releasing oxygen into the air. By the Neoproterozoic era, simple multicellular organisms were emerging. Soft-bodied life drifted in coastal waters, feeding in a world still dominated by microbial ecosystems. The atmosphere was different from today. Carbon dioxide levels were higher, helping maintain warmth under a fainter young sun. Earth's climate system depended on a delicate balance between volcanic emissions, chemical weathering of rocks, and oceanic carbon storage. It was a stable equilibrium, but not an unbreakable one, because on a planet governed by feedback loops, even small shifts can begin a chain reaction. And somewhere in that balance, something changed. The collapse did not begin with a single dramatic event. It began quietly, through chemistry. Over millions of years, the arrangement of continents shifted toward equatorial regions. When land masses sit near the tropics, rainfall increases and chemical weathering accelerates. Rainwater absorbs carbon dioxide from the atmosphere, forming weak carbonic acid that reacts with exposed rock. This process locks carbon into minerals, which are eventually carried to the ocean and buried as sediment. Carbon dioxide is a greenhouse gas. Remove enough of it, and the planet cools. As volcanic activity failed to replenish atmospheric carbon dioxide at the same pace, global temperatures began to decline. At first, the change was subtle. Glaciers formed at high latitudes. Ice expanded seasonally. But ice has a powerful property. It reflects sunlight. The more ice that forms, the more solar energy is sent back into space. This is the albedo effect. As ice sheets grew, they reflected more sunlight, which cooled the planet further, which allowed more ice to form. A feedback loop had begun. What started as gradual cooling accelerated into runaway glaciation. Oceans began freezing from the poles downward. Sea ice crept toward lower latitudes. The planet crossed a threshold beyond which recovery became increasingly difficult. The Earth was no longer adjusting. It was tipping. Asterisk, as the feedback intensified. The transformation became irreversible. Glaciers pushed beyond temperate latitudes. advancing across ancient shorelines and grinding continents beneath kilometers of moving ice. Ocean surfaces began to freeze over completely. At first, seasonal ice thickened, then permanent sheets formed. Eventually, a frozen lid spread across the seas. Sealing them from the atmosphere. Models suggest that ice may have reached within 10 degrees of the equator, possibly encasing even tropical waters beneath thick, reflective crusts. From space, Earth would have appeared almost entirely white, a planet transformed into a frozen sphere. With most of the surface reflecting sunlight, global temperatures may have plunged to -40 degrees Celsius or lower at the equator. Winds swept across barren, glacial plains. Snow accumulated where once waves had broken against rock. The oceans did not freeze solid to the bottom. Geothermal heat from Earth's interior kept deeper waters liquid. But above, a rigid shell tens to hundreds of meters thick separated the surface from the life below. The hydrological cycle slowed dramatically. Evaporation diminished. Precipitation fell mostly as snow. For the first time in its history, Earth's climate system had entered a near-locked state. The world had become still. Asterisk on the surface, the planet appeared lifeless. Winds carved frozen deserts. Glaciers ground mountains into powder. The horizon was a line between white earth and pale sky. Yet beneath the ice, life endured. The oceans, though sealed above, remained liquid in their depths. Heat from Earth's interior rose through the crust, maintaining pockets of warmer water near hydrothermal vents. In these dark environments, microbial communities thrived, drawing energy not from sunlight, but from chemical reactions between seawater and volcanic rock. Near the edges of equatorial ice sheets. Thin zones may have formed where sunlight penetrated fractured ice. These marginal refuges could have supported photosynthetic microorganisms. Even beneath thick ice, light filtered faintly through translucent layers, allowing limited biological activity in some regions. Life during Snowball Earth was simple but resilient. Microbes adapted to extremes of temperature and salinity. Some may have survived in brine channels within sea ice itself. Microscopic veins of liquid trapped between crystals. The biosphere shrank dramatically. But it did not vanish. For millions of years. Evolution slowed but did not stop. Organisms persisted in isolated pockets, enduring a planetary winter that may have lasted 10 million years or more. The Earth was frozen, but it was not dead. Asterisk for millions of years. The frozen equilibrium held. The atmosphere above the ice grew increasingly dry and thin of moisture. With most of the ocean sealed, evaporation nearly ceased. Storm systems weakened. Precipitation slowed to a whisper. The planet existed in a kind of climatic suspension, locked between sunlight and reflection. But beneath that stillness, invisible processes continued. Volcanoes did not stop erupting. Tectonic plates did not cease their motion. Carbon dioxide, released steadily from Earth's interior through volcanic outgassing, continued to accumulate in the atmosphere. Normally, rainfall and weathering would remove this gas, locking it back into rock. But under global ice cover, rainfall was scarce and exposed rock surfaces were buried. The carbon cycle had been interrupted. Slowly, over millions of years, greenhouse gases built up in the sky. Carbon dioxide concentrations may have risen to levels dozens, perhaps hundreds of times higher than today's atmosphere. The frozen surface reflected sunlight, but the air above was quietly thickening with heat-trapping gas. The planet had entered a paradox. The colder it became, the more it prevented the processes that normally cool it further. Snowball Earth was stable, but only temporarily. Beneath the silence, pressure was building. And eventually, that pressure would break the ice. Asterisk, the thaw did not begin gently. For millions of years, volcanic carbon dioxide had accumulated above the frozen world, turning the atmosphere into a tightening blanket. The sun, still shining as it always had, finally met an air thick enough to trap its warmth. At first, the change was subtle, slightly warmer seasons near the equator, faint weakening of ice at vulnerable edges. But once melting began, the balance shifted rapidly. Ice is Earth's mirror. Remove a portion of that mirror, and the planet absorbs more sunlight. Absorb more sunlight, and more ice melts. The feedback loop reversed. Dark meltwater pooled on the surface, absorbing heat far more efficiently than snow and ice. Cracks widened. Margins retreated. The first open water, appearing after millions of years, was not calm. It was a signal. The planet had crossed a threshold. As the ice line pulled back, exposed ocean began evaporating again, reawakening storms and precipitation. Temperatures rose sharply. What had been a frozen equilibrium collapsed into a runaway greenhouse swing. Some models suggest Earth may have moved from deep freeze to extreme warmth in a geologically short time, thousands of years. Perhaps less. The atmosphere, overloaded with carbon dioxide, drove a heating event so intense that it did not merely melt ice. Transformed the planet. The snowball was breaking, and the world that emerged would be unlike anything that came before. Asterisk. When the glaciation truly began, it did not resemble the slow retreat of modern ice sheets. This was release stored tension, breaking all at once. As sunlight finally reached widening patches of dark ocean, heat poured into the planet's surface. Ice cliffs collapsed into the sea. Meltwater raced across exposed rock, carving channels through landscapes that had been locked beneath glaciers for ages. The hydrological cycle returned like a storm after silence. Rain fell on bare continents. Rivers swelled. The atmosphere, heavy with carbon dioxide, drove warmth across latitudes that had not seen liquid water in millions of years. But the melting carried a deeper consequence. As glaciers retreated, they exposed fresh rock to chemical weathering at an enormous scale. Rainwater, now abundant, began pulling carbon dioxide out of the atmosphere again. Dissolved minerals washed into the oceans in vast quantities, altering seawater chemistry. This process helped end the greenhouse extremes, but it also triggered dramatic changes in marine environments. The oceans, once sealed and starved of mixing, were suddenly exposed to oxygenation, nutrients, and turbulence. Ancient waters shifted. New currents formed. The planet began to breathe again. From orbit, Earth would have changed rapidly, from nearly pure white to streaks of blue and dark land, as if life itself were repainting the planet in real time. The Snowball Earth was ending, but its aftermath was only beginning. Asterisk. When the ice withdrew, it revealed a world fundamentally altered. Continents scarred by glacial erosion lay stripped and raw, their surfaces ground flat by moving ice. Sediments carried by meltwater settled into shallow seas, forming thick layers that geologists today identify as cap carbonates, distinctive rock deposits that mark the abrupt end of global glaciation. These formations are silent signatures of a planet that had swung from deep freeze to extreme warmth. The oceans, once layered and stagnant beneath ice, were suddenly reconnected to atmosphere and sunlight. Nutrients released from weathered rock flooded into marine systems. Iron, phosphorus, and other elements mixed into surface waters, stimulating biological productivity. For millions of years, life had persisted in constrained refuges. Now it faced open oceans and newly stabilized climates. Ecological niches expanded. Evolution accelerated. Snowball Earth did not simply test life's endurance. It reset the environmental stage. It rearranged ocean chemistry, atmospheric composition, and the distribution of nutrients. The aftermath created conditions that may have allowed complex multicellular organisms to diversify more rapidly. The frozen crisis had compressed the biosphere into survival mode, The thaw opened it into possibility. Planet that emerged from the ice was not merely warmer. It was primed for transformation. Asterisk. In the wake of global glaciation, the chemistry of the oceans shifted in ways that may have reshaped life itself. As glaciers retreated and weathering intensified, vast amounts of nutrients entered marine ecosystems. Increased phosphorus availability likely stimulated photosynthetic productivity. With more photosynthesis came higher oxygen production. Although oxygen had been present in the atmosphere long before Snowball Earth, fluctuations in ocean chemistry after the deglaciation may have allowed oxygen levels in surface waters to rise more consistently. Oxygen is not simply a gas. It is a threshold. Higher oxygen concentrations allow cells to generate more energy. More energy enables greater complexity, larger body size, multicellular coordination, tissue differentiation. In the tens of millions of years following Snowball Earth, the fossil record begins to show increasing diversity of soft-bodied organisms. Particularly during the Ediacaran period, these early multicellular life forms were not yet animals as we know them. They were strange, quilted, frond-like organisms drifting along ancient seafloors. Yet they represent a turning point, life experimenting with new forms, structures, and ecological interactions. The long winter of Snowball Earth may have acted as an evolutionary filter, compressing diversity before allowing it to expand again. From global freeze emerged a biosphere, poised on the edge of something unprecedented. The groundwork for the Cambrian explosion was quietly being laid. Asterisk. The world that followed Snowball Earth did not immediately erupt into complexity. The transformation unfolded across tens of millions of years. Yet the trajectory had shifted. During the Ediacaran period, beginning around 635 million years ago, the oceans hosted communities of soft-bodied organisms unlike anything seen before. These life forms spread across continental shelves in shallow seas enriched by nutrients and oxygen. Their shapes were alien to modern eyes: flat discs, ribbed fronds, branching forms anchored to the seafloor. They left faint impressions in sediment, delicate records of a biosphere exploring structural innovation. The aftermath of global glaciation had altered ocean circulation, chemical gradients, and ecological opportunity. Life was no longer confined to microbial mats alone. Energy availability had increased. Environmental instability had forced adaptation. Then, around 541 million years ago, the fossil record reveals something extraordinary. The Cambrian explosion marks the rapid diversification of animal life, with most major body plans appearing within a relatively short geological window. Hard shells, segmented bodies, purgation, mobility, complex ecological interactions took shape. Snowball Earth did not cause the Cambrian explosion directly, but it reshaped the planet in ways that made such complexity possible. The deep freeze may have acted as both bottleneck and catalyst, pruning life before allowing it to expand into new ecological architectures. From planetary ice came biological experimentation. From silence came diversity. And the world was never simple again. Asterisk. Snowball Earth was not a brief anomaly. It was a planetary threshold. It demonstrated that Earth's climate system can tip into extremes far beyond modern experience. It revealed the power of feedback loops, how ice, sunlight, carbon, and geology interact in delicate balance. The same processes that once drove the planet into global glaciation later pulled it back through greenhouse warming. Stability on geological timescales is not permanence. It is motion restrained by equilibrium. The frozen interval of the Neoproterozoic did not erase life, but it compressed it into survival. When the thaw came, ecosystems expanded into a world chemically and physically transformed. The scars of glaciation are still visible in ancient rock formations found in tropical regions. Today evidence that ice once reached latitudes that now host coral reefs. Snowball Earth stands as one of the most dramatic demonstrations of planetary resilience. The Earth nearly locked itself into permanent freeze, yet internal forces and atmospheric chemistry prevented eternal ice. The episode reminds us that climate is not static background. It is an active architect of biological possibility. Entire evolutionary pathways can hinge on shifts in temperature, hence, atmospheric composition. The frozen world did not end life, it reshaped it. And in doing so, it helped prepare the stage for everything that followed. Asterisk, there are moments in Earth's history when the planet seems to test its own limits. Snowball Earth was one of those moments. A world nearly sealed beneath ice, oceans isolated from sky, life compressed into scattered refuges. The balance between sunlight and reflection, carbon and rock, ice and ocean tilted so far that recovery seemed improbable. Yet the planet endured. What makes this event extraordinary is not only the severity of the freeze, but the precision of its reversal. Volcanic outgassing continued. Carbon accumulated. The greenhouse intensified. The same geological engine that helped trigger instability ultimately restored warmth. Earth's deep interior became the agent of its survival. In this cycle lies a profound truth. Our planet is dynamic, self-regulating over immense spans of time, yet vulnerable to thresholds. When those thresholds are crossed, change can be absolute. Snowball Earth may have been the most extreme climate state of the last billion years. It reminds us that habitability is not guaranteed. It is maintained through delicate interplay between atmosphere, geology, and life itself. The frozen sphere that once reflected the sun, almost entirely white, eventually became the blue world we recognize today. Not because it was stable, but because it adapted. Asterisk. To comprehend Snowball Earth is to confront the scale of deep time. This was not a winter measured in seasons, nor even in centuries. It endured for millions of years. Generations of microorganisms were born and died beneath ice that never retreated. Entire evolutionary experiments unfolded in darkness. Unaware of the sky above. When we look at ancient glacial deposits in Namibia, Australia, or Canada, rocks formed near the equator that bear the unmistakable scars of ice, we are seeing evidence of a world fundamentally different from our own. These formations are quiet witnesses to a planet that once froze almost entirely, yet carried life through the freeze. Deep time humbles human perspective. Civilizations rise and fall within thousands of years. Snowball Earth lasted long enough for continents to drift and mountains to erode. And yet, the processes that drove it, carbon cycles, volcanic outgassing, albedo feedback, are not relics of the past. They are active systems still operating today. The frozen Earth teaches that climate can swing between extremes. But it also teaches that life is persistent. When given even the narrowest refuge. In that persistence lies the thread that connects ancient microbes to every complex organism that followed. The ice came close to silencing the planet, but silence never became extinction. Asterisk. Snowball Earth was not the end of the world. It was a crucible. For millions of years, the planet stood on the edge of sterility, its oceans sealed, its continents buried, its climate locked in reflective silence. And yet beneath that silence, chemistry persisted. Heat rose from the interior. Carbon accumulated in the sky. Life endured in darkness. When the thaw came, it did more than melt ice. It rewrote possibility. The world that emerged was chemically enriched, oxygenating, unstable in ways that fostered innovation. Within tens of millions of years, life would experiment with structure, movement, predation, vision. The Cambrian explosion would not occur immediately. but its foundations were laid in the aftermath of global ice. The Earth nearly froze into permanence. Instead, it transformed. From a white sphere reflecting the sun into space, it became a dynamic blue planet, capable of hosting forests, oceans, animals, and eventually, minds capable of remembering its past. Snowball Earth reminds us that catastrophe and creation are not opposites in deep time. They are chapters of the same story. If this journey into one of the most extreme episodes in Earth's history expanded your perspective, consider subscribing to the channel, leaving a like, and sharing your thoughts below. Which turning point in planetary history should we explore next? The Great Oxidation Event? The Permian mass extinction? The rise of the first forests? The Earth has rewritten itself many times. And we are only beginning to understand how.